Alright, so now we are experts on the Newton-Raphson method and we are going to use it to solve some equations and draw some graphs. Let us consider this equation. X plus 0.1 sine x equals y plus 0.2 cos 3y. Okay, so in the xy plane there's some curve. I don't know what it is. I want to plot it. For some specific x, like x equals 1, say, this is almost 1, this is almost 1, so maybe y is not far from 1. I can solve this equation y. You can solve it for y using Newton-Raphson. So let me go to Matlab, open, cancel, new, here's a new file, and I say function z equals junk y, and I say x equals 1, and then I say y plus 0.2 times cos 2 times y. I think that's my equation. No, cos 3 times y minus x minus 0.1 times sine x. Given x, what is the y for which this is 0? This is in some function suitably called junk, because I don't really care about this too much. I save it as junk. I come here and I say Newton junk, and I give it an initial value of 1.1 or something. Well, that didn't work. That's because this is not assigned to anything. So I say z equals, that's the quantity that has to be made 0, and when I do that, then I get my answer. So that is my y equals answer. Let me do format long, and that's my answer. Okay, I can check. I can say junk of y, and indeed it is very small because Newton-Raphson has given me a solution. Now my question is, how do I draw the entire graph? In this case, I can draw it using a trick, and the trick is like this. I can differentiate this expression with respect to x, and when I do that, then I get 1 plus 0.1 cos x minus y prime plus 0.6 sine 3y times y prime. I shouldn't have done this. I'll do this here, erase this part and put minus. Okay, which is now a differential equation for y. So I have y prime equals 1 plus 0.1 cos x divided by 1 minus 0.6 sine 3y, and I have chosen these coefficients in such a way that I don't have trouble. You see, the denominator does not become 0, things like that. I just want to show you a simple example. Alright, so let's go back to Matlab, 1 plus 0.1 cos x and so on. So I come here to Matlab, and then what I do here is now I am writing it in a differential equation form. Okay, so I will say x comma y, this is the independent variable, this is the dependent variable. I will come here and I will say this is actually dy dx. That's what I mean. This is y prime, and I will say dy dx is equal to 1 plus 0.1 times cosine of x divided by 1 minus 0.6 sine 3y. 0.6 times the sine of 3 times y. You should look into ODE solution in Matlab. This is the independent variable. Sometimes it is time, but here it is just x. This can be a vector. There can be 2 or 3 or 4 state variables. There is no real difficulty. And this is dy dx. I have to give it an initial condition that is on the line, and that is the only thing I need to care about. When I solve ODEs, I have to set the tolerance. Okay, so this is a command you need to know. I have used this in the past. Let me use -7. That is good enough. You should learn this command. Okay, my initial condition is this y here. I will call it y0 is equal to y, just to, that's my initial condition, and x is 1. Okay, so let me now say xy equals ODE45, which is Matlab's, and the file is still junk. Matlab's built-in file for solving ODEs, and let me solve for x from 1 to 10. Give it an initial value y0 and the error tolerances. Okay, so it solved it, and now I can plot y against x, and you see that is the solution. And x continues indefinitely, and I can solve this differential equation for as long a time as I want. There is no real difficulty here. Okay, so this is one thing to do. Now we'll take a more difficult problem. Okay, so what we will take now is this problem. Let us take this problem. X square plus y square plus 0.1 sine x is equal to 1. So why have I done this? I've done this because now it is not a perfect circle. Okay, I can change it a bit actually. Come to think of it, I can make it 0.1 sine xy equals 1. This is a slightly deformed circle, but it is still not easy for us to solve for y in terms of x or x in terms of y. Now what we can do is we can introduce, see, we can try the old game. And we can say 2x plus 2y dy dx plus 0.1 cos xy 1 times y plus x times dy by dx. That's the derivative of the left hand side equals 0. We can solve this for dy by dx and solve the differential equation for y as a function of x. But because this is some kind of perturbation of the circle, as x increases, the solution is going to turn around. There won't be a solution for x larger than that. There will be a singularity and the calculation will crash. Okay, so there is another way to do it, and the other way to do it is to play a trick. And the trick is to say I will introduce some other auxiliary variable like a parametric plot. I can call it t, I can call it s, doesn't matter. Over here I'll call it t. I will think of x as a function of t, I will think of y as a function of t, and t will go forward in time, or whatever t is will increase, and x and y will keep tracking this curve. When I do this, then my derivative looks different, right? So then my derivative, then it looks like 2x x dot plus 2y y dot plus 0.1 cos x y x dot y plus y dot x is equal to 0. Now this is a system of two differential equations that we want to deal with, only we have one equation. Okay, so this is the tricky part. If you think about it slowly, you will understand the trick I am going to play, but first I have to write it in some form that is easy. So what I will do is I will collect the x dot parts and the y dot parts. I have this equation here. So what I will say is 2x plus 0.1 cos xy times y. This is one element, and the other element is 2y plus 0.1 cos xy times x. This thing times x dot and y dot is equal to 0. If I was playing my old game where actually I was just thinking of y as a function of x, then basically it is like setting x dot equal to 1. So added to this system, I can add x dot equal to 1, and that would be the old method. But we want a new method which allows the curve to turn around. We want a new method which allows the curve to turn around. Okay, so what is the new method now? The new method is to say that this vector x dot y dot dotted with some vector v is equal to 1. So that this is to be chosen. How do I do that? So it's a little trick I'm playing, and here is how it works. So let's say this is x, this is y, and my curve is going in some way like this. Now over here, instantaneously there is some rate. What I want is something that is approximately equal to this rate. So I make a new vector v. So what I say is I denote q is equal to x dot y dot. Then I say v dot is equal to, and I put some big gain weight number, some number which we will choose, a biggish number, and then I will say q by the norm of q minus v. Okay, this is a new differential equation that I am making up. What happens is, as q changes slowly and this gain is some big number, v is always very close. It always gets driven to the unit vector along q. And then I will have my equation which is q dot transpose v should be 1. That is the dot product. This is the dot product part. So let me show you how this all works. Let me get this equation here first, because that is the old part, and then we have to get a solution. So we'll try x equals 0.5 or something, and we'll see what happens. So let's come here to Matlab. Not that. Let's come here to Matlab. Once again, I will now call this z because this function is just junk. Given x, I have to find y. So I will come here and I will say x equals 0.5. That's some number, and for that we will try to find y, and what we will say is z is equal to, let's go look at our equation, x squared plus y squared plus 0.1 sine xy, x squared plus y squared plus 0.1 times the sine of x times y minus 1. Y minus 1, here's the minus 1. Okay, so that is what has to be 0. So for given x equals 0.5, we have to find a y for which this is 0, and we can hope that this is something not very far from the circle, so maybe 0.8 or some such number, we'll see. Okay, minus plus whatever it is. So we'll come here, we'll say Newton junk, and this is the guess for y that we are now giving, and we'll try 0.8. Okay, so there's an answer, 0.84. Okay, so we'll say y equals that. In fact, what I will say is Q0, my initial condition, is 0.5 and y. All right, very good. Now I will let's see now. This is Q0. V we have to find out. Let us see how that goes. Let us come here to this equation here and let's get an initial value. Okay, so here's the initial value is, let me use yellow here so that I can write directly over here and it will not be a problem. You see, so I'll come here. This is the rate. If x dot is 1, then this is y dot. Okay, this is dy by dx. Or if we can come here, you see this equation, if you put x dot is equal to 1 in this equation, then you will get that equation. Okay, so we come easier to just come here and put x dot is equal to 1, and so it is easier for us. What we will say is y dot is equal to the negative of this, so we will compute that. Okay, so we'll come here, 2x plus 0.1 cos xy times y. Let's come here, let us say y dot is equal to 2 times x plus 0.1, 0.1 times the cosine of x times y with a negative sign over here, and then divided by that. So here's a negative sign divided by 2 times y plus 0.1 times the cos of x times y times x. Okay, so this is what y dot. Now that didn't work. Why didn't it work? What is x? X is some big thing. X is equal to 0.0. X is equal to 0.5. Y is that. Okay, so y dot is that. Now it worked. And then my rate, the original q dot, is like this. Q dot is equal to 1 and y dot, but of course I want it to have unit norm, so I will say v is equal to q dot by the norm of q dot, and that is the initial condition for v. And now my full initial condition is q0 is equal to q0 v for the differential equation that I am going to show you. So the differential equation that I am going to show you, we will write it here now. Let's see now. This is the one. This will help me. So I will come here now and I will say A is equal to, I'm just cutting and pasting here to save myself some trouble. I hope you realize I'm just putting the comma here, and that is the first part. So this is the part that will multiply x dot, this is the part that will multiply y dot. This times x dot plus that times y dot is going to be 0. Okay, now the second part is A. So x and y have to be defined here. So I have a problem. X, I have to give it an initial t, which is my dummy variable. X equals y1, v equals y3 to 4, and y equals y2 only, the second element. Okay, after we do this, now this one, x dot and y dot, will be determined from here. My other equation, so this is, and my A is going to be A semicolon. In the next row I am putting V transpose. Alright, and then I have B, which is equal to 0, because the first, from the first equation it is 0 and the second one is 1. That's not true. That is true. Okay, so that is true. And what this gives me is, it gives me a Q dot is equal to A backslash B. I still need a V dot, and the V dot is equal to this number G, which I have to specify. So I'm going to put here G equals 10 for the moment. G times Q dot by norm of Q dot minus V, and this should work. There is giving me a problem because this is not needed. Okay, all right, let us see the correspondence between these equations. Look at this part. This part will be multiplied by x dot and y dot and will be set equal to 0. That is this equation here. This equation here. That is this. Let's try red. That is this equation here. Okay. That is this equation here. Now, this is the second part. That is the next equation. I need two equations in x dot and y dot to determine x dot and y dot. That is the other equation. This is a made up condition. It is a rate normalizing condition that gives me an x dot and a y dot. And now I am just calling that vector q dot, and then I am, there is a problem here. That's correct. No, that's not correct. This is what is correct. Okay, that's what I had before. So now over here what happens is, this largish gain drives this V towards a unit norm vector in the direction of q dot. Okay, so let us see how that works. My initial condition is given. Let's try it and see. Let us say t and some arbitrary vector q is equal to ODE45 junk, which I have saved. Initial conditions. Now initial conditions don't matter. I'll try 0 and 20 or something. It will be fine. And then my initial, sorry, this is the time interval. That doesn't matter. The initial condition is very determined. There is no question. Okay, so initial condition is Q0 OP. Alright, something needs to be specified. Of course it does. Over here it is Z. Z is equal to Q dot V dot. that worked. So if I look at plot of q versus t, then I'm getting this oscillatory sort of solution. Several things are there, but what I'm really interested in is y versus x. So I am interested in plot y all rows first column against y all rows second column. Oh, q, sorry, you can see that Matlab is filled with traps like this. You have to be careful too, but here it is, and it's not a perfect circle. For example, if I do axis image, then it will scale the x and y axes perfectly, and you see that it is a slightly distorted circle. Okay, it has gone round and round many times. Now the question is, what was the importance of this value gain, g? It does not have much importance. For example, if I make it 6 and then I say here hold on, and then I do the same solution, and then I plot this curve again, only this time I plot it in red, you will see that it is the same curve. There is just no difference. I can zoom in over here endlessly, no problem. Okay, it is the v that is different. So if I plot t q axis equal is a problem because of hold on. Let me see, there are actually several curves in here. There are 1, 2, 3, 4 curves in here, and that's the problem. 2 of them are approximately equal to the rates, and 2 of them are actual variables x and y. Okay, so there is a lot for you to think about in here. Please think about it before watching the next video, where we will use these ideas to find out motions of linkages. Thank you.